Hello students. So today we will discuss about cantilever geometric nonlinearity, large amplitude resonance, and mainly this formation of this cantilever is done with nano wires, and it is a nano electronic device or nano electronic mechanical systems, and we will be mainly focusing on how to utilize this property in making fast nanoelectric devices, switching devices. Now, this system is characterized by flexible components, and it has got large electrostatic voltage load. And also it is nonlinear terms are actuated. Uh, the nonlinear application of nanobeams and electrostatic actuation has got application in biomass sensors. Application. So these properties, especially this electrostatic nonlinear actuation, this has got application in biomass sensors. Now, the dimensionless parameter associated with MEMS device. So, this dimensionless parameter, this dimensionless parameter is given as delta equal to G0 by L whole square. So what actually this G0 is? So we write it once again. It's delta equal to 0 by L whole square, where L is the beam length, and G0 is the initial gap between fixed and movable electrodes. And delta is the nonlinear impact factor. This is a thing that is called the nonlinear impact factor. If this is the cantilever, this is the cantilever, and this is the clamp region. So this is the fixed region. This is the movable part. There is a fixed part. So this distance is G0, and this is the beam length. So this is L. Now this system has got four different categories of effect. Four different categories of effect of electrostatic actuation. Electrostatic load, whatever you want to call it, and impact, and its impact on this non-linearity. That means this delta. So let's take up one by one. So we actually can put a voltage across this cantilever. So we are putting a voltage, electrostatic voltage, between the fixed and the fixed and movable part. Now when the value of this delta is much less than 1, that means when L is much greater than G0, that means the beam cantilever beam length is much higher than the total distance of its movement, then we call it soft excitation. So when L is extremely large and compared to that, the G0 is very small. G0 is very small compared to L. And this also corresponds to weak nonlinearity. However, so the first case, in here also, if the voltage applied is also very low, then the total excitation. So this is gate 1. Both the non-linear impact factor and the voltage applies, both are very less. The second case is so if voltage applied is also low, we are also calling it soft in terms of the voltage applied. So in both cases, the nonlinearity and the impact factor at the voltage, both of them are soft. If, however, the nonlinearity is not that less than 1, but little less than 1, then it's called a strong nonlinearity. Call it a strong nonlinearity, and if the voltage applied is hard, this is one of the cases. The third case is when This is weak nonlinearity, whereas the voltage applied is hard. And the last case is when this is a strong nonlinearity and the voltage applied is also strong. So these are the four different cases, strong, or you can call it hard. Now, what we are doing, we are trying to make the switch based upon gold nanowires. We're using gold atoms to making the nanowire switches, and we'll be doing some local heating on gold single atom chains. So whenever we are putting in such a system, the large current, since this is a nanostructure, since we are dealing with a single strand of atoms, so this is a nanostructure, so application of this heat will cause large current density. So initially there is a large current density associated with such gold chains. There is large current. Use a different color. There's a large current density. Nanostructure, and there is high charge scattering rates due to this global heating. And this may lead to the device failure. So there are two things. First of all, since there is a gold atom, so there is high current density, and since we are applying local heating, so it is causing, local heating may cause the atoms to come in align together, but they are causing high scattering rates. Now, what we are focusing on, we are focusing mainly on the nanojunction thermal conductivity. So, next is your nanojunction thermal conductivity. This is our main focus. And we, in this system of this nanowire devices, and there is a repetitive formation and breakdown of this nanojunction. So this is associated with repetitive junction formation and breakdown. This this formation of junction formation and breakdown becomes more active when we are applying an AC voltage. this goes more active. Now at this stage, when you are applying AC voltage and there is formation and breaking out this nanojunction, the conductance G is less, it goes down due to rate of formation and breakdown of the nanojunction. So we have basically, and there is gold wires. So formation of say AU atoms like this. Now the conductance, this decrease in this conductance is again stepwise. Now, as G eventually drops to 0, as G eventually goes to 0, drops to 0, the piezoelectric retraction, piezoelectric is some piezoelectric actuator. So since remember that we are now dealing with cantilever beams, so we are associating with this, making this cantilever with the help of these gold atoms. Now, so there is a piezoelectric actuation involved. So these piezoelectric actuators are attracted to reconnect the junction. They are attracted to reconnect the junction. And so that the conductance G, this again is now greater than 10 times the Landauer's conductance, or the minimum possible conductance. And this is also called the quantum conductance, G0. So this is basically 2e square by h, this G0, and it's called Landauer's oblique quantum conductance. Okay. Now let us draw the gold atom junction once again. So this is the gold atom junction. The AU junction, AU nanojunction, and here voltage has been applied, and AC voltage has been applied, sinusoidal voltage, and of frequency 1 megahertz, and the amplitude is 0.05 volts. So the amplitude denoted by VPP is 0.05 volts. So this is the amplitude. Now, as we said that the G goes down in steps, So if we plot conductance versus time in seconds, and say this is G expressed in terms of G0, so we can see that, and so this is 5 and this is 10. So the plot will be initially, there will be a step down right. So this is where the G tends to 0 and there is a repetitive formation and breakdown. So at this point the G is almost equal to 0. Now this is where we can say that the nano junction has broken. It is broken. It means this is what has taken place. Right, so there is a breaking down of this junction. At this point, the piezoelectric again retracts and connects with the junction. So suddenly there is a shoot up of the conductance to 10 times G0 value. So it will again shoot up. This is where the connection is again re-established, connection formed. And again, this atoms form again a junction, and the process continues. Again, it really comes down, and the process continues as since we're using an AC voltage. So there is a spontaneous breakdown at room temperature and vacuum. Effective velocity, effective voltage is VPP, amplitude voltage, by root 2, and the effective temperature, TFF is the effective temperature, and then it is equal to T square plus alpha T square plus alpha V effective whole square to the power 1 by 2. Where alpha is a constant. And its value is 280 k square by V square. So we plot the effective temperature. So this is the effective temperature. We plot it again with respect to voltage. So T effective plot with respect to V effective. So this is 280 This is 290, and this is expressed in Kelvin, and this is 340. So the plot will be parabolic in nature. So the plot is, and this will correspond to 0.1, this is 0.7. So it can be visualized as formation of two junctions. So we can say that this K stands for the thermal resistance, and so we can draw it in this following fashion. We can say that there is thermal resistance. This is 1 by C. For the first part of the junction, there is formation of junction, right? So there is a initial temperature T0 associated with the first part, T0 and T0, and these are 1 by Kc and 1 by Kc. So there is formation of junction here. So it is 1 by Kc is nothing but the thermal resistance, so at room temperature, at heat dissipation, when there is heat dissipation, the EU single atom contacts, and so we can say that at room temperature, the heat dissipation causes the cold atoms gold single atoms contracts, where the heat source has an effective temperature whose sides are connected to two sinks. At the ambient temperature, T0. So again, this is what is represented as we have said. So initially there are two sinks, 1 by Kc, with ambient temperature T0. So this T effective is the heat source. This is T effective. It has two sinks, so it sinks down at these two levels. Now, if we assume in this whole system, if we assume that a steady state heat dissipation has taken place, the energy balance, when there is an energy balance, and so based on that, there is an equation which says that rho C is equal to 2 kg delta T. Now this rho C is nothing but transport of energy per unit time. So there is a transport of energy per unit time. So this is the amount of energy which is dissipated at single atom contacts. And it is dissipated to the heat sinks by thermal conductance 1 by Kc, as explained earlier, along the temperature gradient. So dissipated to the heat sinks via the thermal conductance Kc. So 1 by Kc is the thermal resistance, so Kc is the thermal conductance. So we can say via thermal conductance Kc along the temperature gradient. By temperature gradient, we mean that the difference in temperature. So that is a delta T, T effective minus T0. The T0 is the ambient temperature. This is the ambient temperature, and it is 290 K. And as mentioned, so in the diagram, T effective versus V effective. This is the lowest temperature. This is where the TO is at 290, and alpha, as in this case, is a constant which is equal to 280 K square by V square. So it can be understood that the heat generated at the single atom contacts is dissipated, and so heat that is generated at a single atom contacts is dissipated mainly through thermal conductance. The equation is Kc is equal to KEL plus KPH. EL is electronic and pH is photonic. Conductance, electronic conductance. This is electronic. This is photonic. Now at in low temperature, that means when T is much less than the ambient temperature of 290 K. So this is dominating. By low temperature, we mean that it is less than the divide temperature. So in that case, KPH is proportional to T cube. Now, for metallic junctions, the electron travels between the electrodes by resonant tunneling. Like in this case, got the gold atoms. So there will be tunneling across the device. Resonant tunneling. Electron travels through the resonant tunneling, and for that case, the electronic conductance is much higher than the photonic conductance. So this actually validates the Wiedemann-Franz law. Kc is equal to L G into T. So this thermal conductance, this is a constant. So this electrical conductance is insensitive to temperature and wire length. So indicates that G is insensitive to temperature and the wire length. That means this length they are talking about. Now plotting the phononic conductance, not photonic, phononic conductance with respect to, and the unit of this phononic conductance is nanowatt per Kelvin. This is the unit. So we plot it with the number of atoms n. In the junction, that means this n is actually these are the gold atoms arrangement. So n is basically number of atoms through which the electron can pass when it is moving through the junction. So in this case it is 1, 2 and 3, so here n is equal to 3. So longer we make the chain longer, the more there will be number of atoms. So it is basically signifies the length of the chain or the length of the wire. So this is a nano wire formation take place. So that indicates the length of the wire. And say and the value stands for, say, from here it's 2 to 12. So you see that the plot takes a shape like this. So as the number of atoms increase, the phononic conductance decrease. So as n increases, kph is found to decrease. And if you plot, on the other hand, if you plot the conductance, electrical conductance, with respect to again n, so it's almost a constant value. So there is less difference on the number of atoms on this electrical conductance. Now, I previously mentioned that this is what is happening at low temperature. So, why low temperature? We meant that when the temperature is much less than Td, the desired temperature. So for gold nanowires, the Td value is around 100 Kelvin, and for normally for bulk gold, when it is not in the shape, not in the nanostructure, the Td value is little higher. It is 160 Kelvin. So there is a decrease in Td value when we go to the nanostructure. Now, plotting again the phononic conductance with respect to temperature expressed in Kelvin, say from 0 to say 500. So we see the following shape of the plot. Increases with little undulations. So not exactly like this, but it basically tries to attain a constant value. So kph observed to tends to attain a constant value, and so it is leading to the classical behavior. At high temperature conductance. So this is what is happening when the temperature is greater than equal to the desired temperature of 100 Kelvin. So say this is the value. Say this is 100. So after 100, say it is trying to attain a constant value, tends to attain a constant value. Now, at lower temperature, for example, if we talk about temperatures in this range around say 50 Kelvin, here actually the quantum corrections become important. Now, coming to the Weidmann-Franz law, we know that Kc is equal to Lg into T in the range of T effective. And in this range also the electronic conduction is dominant on the phononic conductance. So we plot the total conductance K in nanowatt per Kelvin with respect to temperature expressed in we plot for both the electronic and the photonic conductance, we will see that the electronic conduction shoots up with temperature, whereas the photonic conductance, it attains a constant value. So this is your KEL, and this is your KPH. Now, the energy dissipation at the nanojunctions and these situations, we had previously written for the steady state form, we had previously written that rho c is equal to 2 kc delta T, this formula we had introduced earlier. So this rho c is the heat dissipation per unit time. So if we plot rho c expressed in nanowatt with respect to rho n expressed in microwatts, which is the internal energy. So we can see that again the plot taking a linear term. So this is 60, and the slope is 0.018. So rho c is 0.0018, the rho initial energy. So with the incident, the incident heat, so with incident heat, the heat dissipation also goes down, goes up. Now, the divide temperature theta d. So this is again can be called, this temperature can be called the temperature of crystal's highest mode of vibration. So it's temperature of crystal's highest normal mode of vibration. And theta d is equal to K m by K. So H, so not sorry. And this is mu m is the frequency of vibration. K is the Boltzmann constant. Now, if you try to understand the phonon contribution to the specific heat of solids, or the resonating modes of sonic disturbances, So resonating modes of sonic disturbances, that means the phononic contribution related to sound or the relation between energy. So the wavelength associated with these sonic or these vibrations, we give it this lambda n, and is a number of nodes, a number of so if we just put a string between two clamps, so n stands for the number of waves created. So this is n is here 1 and 2, n is here is 2 similarly. So the lambda n is 2L by n of the standing waves between two clamped modes, 2L by n. So this distance is 2L. And the energy associated with this again is En, and it is equal to N nu M. So we can also write here En is equal to H nu M, and H is Hc by lambda, and we know that lambda is equal to 2L by n. If we replace, it becomes En is equal to Hc by 2L n. So C, instead of using C here, we will use Cs. So Cs, initially C was the speed of light, so Cs is the speed of sound. So from here again, if we take En square, it is Hcs by 2L whole square into n square. Now n square is equal to nx square plus ny square plus nz square. So total energy, so we are actually assuming it a cube. So initially it was clamped between two ends, so it was one dimensional. So instead of one dimensional, if we consider it three dimensional, so initially it was only n, now there is nx, ny, and nz. So it means the wave is clamped at the three directions. So there is clamping at the three directions. So this is the equation that we obtain. We obtain En square is equal to Hcs by 2L whole square into nx square plus ny square plus nz square. Now the total energy in the box, so there is a cube and there are three sides being clamped and there is sound energy inside it. Now if someone tries to find out the total energy in the box, and then it will be E is equal to summation sign n En n bar En this quantity n bar En is the number of phonons in the box with energy En. Now, a phonon cannot have an arbitrary high frequency, and so its frequency is bounded by the medium of propagation. So, a phonon can't have arbitrarily high frequency, and its frequency is bounded by medium of its propagation. So, if the phonon travels between say two clamps, say this is the first clamp and this is the second clamp. It travels only this much, so we say that this corresponds to n is equal to 1. If again it travels in this way, we say that n is equal to 2. It takes this is equal to 3. So it can take multiple directions. So now n becomes equal to n to the power 1 by 3, where n is nothing but the number of atoms. So in the gold junction, again if you draw the gold junction, so the phononic transfer will also depend on the nodes, or the energy of the phononic transfer. It also depends on the number of atoms, and because En is equal to HCS by 2L into n square. This we already found out. So number of atoms is very important. So in the nanowire, and the nanowire junctions formed. And also the minimum wavelength. So if this is the minimum wavelength, so there are two atoms, atom 1 and atom 2. So the minimum wavelength of a photon is twice the atomic separation. So we know that lambda is equal to 2L by n. So in this case, n is equal to 1. N is equal to 1. So the minimum wavelength of photon, lambda min, is equal to 2L. L is nothing but the distance between two atoms. So these two gold atoms are sitting here. So the distance between them becomes the minimum wavelength of the photonic mode.